Hi guys, welcome back. Today I'd like to uh, move a bit forward with quantum mechanics, a little bit more. So quantum mechanics, because I would like to at some point, maybe next video, discuss the quantum harmonic oscillator in analogy of what I've done with the classical physics. Yeah, but before doing that, I realized that it needs a bit of more math and background to get to the point which we can analyze in very simple level that problem. So the first thing that I want to talk about today is a couple of things. One is the Hamiltonian of the system. So, and then the solution of the wave function, the free moving wave function, Schrödinger equation. So free Schrödinger equation. So let's yes. So what is, first of all, what is an Hamiltonian? So let's step back, think about the energy, and think about Newton's law. So we know that F is equal to ma, and also we know that dx in dt is equal to the speed. Okay, for the moment I've unidimensional, I forgot the arrows on purpose, not to make the notation heavy. So these are vectors supposedly, but we can think about the motion in one dimension only. So think about the free fall of an object, for example, which is happening in the z direction. Okay, in this case we know how to solve the problem, and that's fine. But think about, for example, an object in one dimension, always an object attached to a string of a constant k and displacement x. In this case, we know that force, which is a, is equal to minus kx. Okay, and we also know that dx in the t is equal to the velocity, and this is enough. And if we give the initial conditions, so x0 equal to, for example, 1 meter, and v0 equal to 0, for example, meter per second, with these two initial conditions we can solve this equation easily. Well, easily, depends, but we can solve it, and we saw how to solve it in the video on the harmonic oscillator using sinusoid and cosinusoid. And we did it by solving the differential equation, which is basically dx in the t squared equal to minus kx. And from here we derive the sinusoid and cosinusoid. That's fine, we know how to do that. But there are equivalent formulation of this problem that can be done using the energy. So we can get to the same equation by defining this derivative over, and this was b, and this is d over dq, and then I will put here Hamiltonian, so this is t, and this is t, and this is b, this is h, and then we get another. There are always differential equation, so we're not scared about differential equation, because we know how to deal with them. And let's see if I got the sign right. Maybe not. I will check it now. And the equation of motion is such that we have the kinetic energy plus the potential energy, which is mk x squared, or x squared. Yes. Yes. Or maybe mk. Yeah. Let's see how it works. So basically, we define two functions, kinetic energy and potential energy. And if you remember the kinetic energy, so if you are on the top of a hill, you have some potential energy because you are high on the ground, and then when you roll down, this potential energy reduces in favor of the speed, which will increase. And this is called kinetic part, which depends on the velocity. P is mass times velocity, which is the momentum, and then we divide by mass again, so it's basically 1 over v squared, which is the kinetic energy. The amount, yeah, it's expressed in joule. It's a number that tells you how much energy in the system is due to the fact that it is moving. And the other part is called potential energy, or U, and it tells us how much more energy can be exploited by moving in the x coordinate. Okay, so in this case is a kind of storage energy, so some energy that you can't have just because you are sitting somewhere, but there is the potential to express energy because, for example, something is pushing or something is holding you up, and then therefore you still can express that energy if you remove that constraint, for example, that is holding you or keeping you still. Okay, but apart from the definition, we can see that if we define this function h, which is this, and we okay, q is p is x in this case, so let's put x because it's the position. It could be generalized to angles or other sorry, variable, but in this case is position. So the first one, let's see, we know how to do derivatives. So derivative of p over t is effectively m derivative of v over t, which is the acceleration, and the derivative of, this is a minus in fact, and the derivative of h respect to x is minus, should be 2 minus kx. And if you think about it, this is already ma equals force, right? So this is the acceleration, and this is the force that we had before due to the spring. So we know that. And this other equation down here tells us that velocity, so derivative of space over time, is equal to derivative of h over p, which is, so let's express it correctly. We need to solve it, not to show that it's correct. So derivative of x over t is equal to derivative of this part here over p, and it gets mp. No, sorry, v, mv. Sorry. So derivative of p squared, let's do one step more. It gets 2 times 2 divided p divided by m, yes, which is v effectively, yes. So, and this is the other equation which we have got here. So okay, so this is just a quick calculation to show that if we use this with this Hamiltonian, which is the total energy of the system, we can still be able to solve our problem using differential equation, which is this set of equations here. It's slightly different than this one, but it's more general and can be applied to other scenarios as well. It's a bit more geometric. It does have some nice intuition, because basically it tells you that the energy somehow constrains the motion of your system. It tells us where your system can go, and the energy fixes the trajectory of your system due to the interaction present in the system as well. So it's a nice way to visualize that, but also it's very important because it gives us a bit of intuition on why, and then I can go to the next slide.